Today we're going to talk about one of the most important skills in science, finding real gaps in knowledge and converting them into testable hypotheses. Anyone can search PubMed, anyone can download papers, but not everyone can look at 40 articles and say, this is what is missing. That ability separates students from investigators. By the end of this session, you'll know exactly how to move from literature search to research question in a structured and intelligent way. Most research projects fail not because experiments are poorly executed, but because the question was weak. A weak question leads to incremental science, low-impact papers, rejected grants. A strong project begins with a meaningful gap, a measurable gap, a feasible gap. Learning to identify that gap is one of the most powerful scientific skills you can develop. A knowledge gap is not simply something that hasn't been studied. That's a common misunderstanding. A true gap is more specific. It's a missing link in logic. For example, not cancer and nutrition haven't been studied, but the effect of omega-3 supplementation on inflammatory biomarkers during chemotherapy in stage 2 colorectal cancer patients has not been tested. See the difference? Specificity creates opportunity. There are different types of gaps. Conceptual gaps, we don't understand the mechanism. Methodological gaps, the tools used are outdated or incomplete. Population gaps, tested in mice, not in humans. Translational gaps, strong lab data but no clinical trials. Conflicting evidence gaps, two strong studies disagree. When you review literature, you should actively categorize gaps into these buckets. That makes your thinking structured. After collecting 20 to 50 strong papers, stop searching. Now analyze. Ask, what do most papers agree on? Where do they disagree? What questions are repeated in the discussion section? Often, the authors themselves tell you what is missing. Patterns reveal gaps, not isolated papers. Now we get practical. Create a simple table. Study, model, intervention, outcome, limitation. This exercise is extremely powerful. Within 30 minutes, you'll see patterns. You'll notice, most studies used male mice. Most studies measured weight but not inflammation. Most trials were short-term. That pattern becomes your opportunity. If 20 studies test the same thing in the same way, that tells you two things. First, the topic is important. Second, researchers may be stuck in a pattern. Ask, has anyone tested a different age group? Has anyone changed the dosage? Has anyone tested mechanism instead of outcome? Innovation often comes from small shifts. Science often forgets important variables. Sex differences, age differences, ethnic differences, comorbid conditions, long-term outcomes. If everyone studies young male mice for 4 weeks, that is not complete science. Missing dimensions are powerful gaps. When two strong studies disagree, don't panic. Get excited. Conflicting evidence is where high-impact science lives. Ask, were models different? Were doses different? Were endpoints different? Resolving contradictions can lead to very strong publications. Now let's zoom out. Good research connects two levels. The 30,000-foot view, big global problem, and the microscopic level, specific mechanism. For example, cancer is global. Nutrition in cancer is specific. Omega-3 dose during chemotherapy is very specific. Your gap must connect these two levels. A gap becomes powerful only when written as a question. Instead of, there is limited research on. Write, does intervention X alter outcome Y in population Z? If you can't write it as a question, it's not ready yet. Before getting excited, ask practical questions. Do I have the tools? Is the outcome measurable? Is it ethical? Can this be done in my timeline? A brilliant but impossible question is not useful. Feasible science wins. A strong hypothesis must define intervention, outcome, model, direction of effect, template. If X is applied to Y, then Z will increase or decrease because if your hypothesis does not predict direction, it's incomplete. Let's look at the difference between a weak hypothesis and a strong one. A weak hypothesis sounds like this: nutrition affects cancer. It's broad, it's vague, and it's impossible to test in a focused way. Now compare that to a strong hypothesis. High protein supplementation during chemotherapy will preserve lean body mass and reduce inflammatory cytokines in stage 2 to 3 colorectal cancer patients. Notice the difference. It clearly defines the intervention. It specifies the population. It identifies measurable outcomes. It's specific, it's measurable, and it's testable. And that's exactly what reviewers are looking for. When building a strong hypothesis, you must clearly define your outcomes. First, your primary outcome, the main measurable endpoint that directly tests your hypothesis. Then, your secondary outcomes, additional supportive measures that help strengthen or explain your findings. And importantly, think about alternative outcomes. What will you measure if your hypothesis turns out to be wrong? Planning for different possibilities does not weaken your study, it strengthens it. Science respects investigators who anticipate uncertainty and design experiments thoughtfully around it. Now let's apply this framework step by step. Start broad. The topic is cancer. Now zoom in. Nutrition in cancer. Zoom further. Dietary supplements. And from here, instead of asking a vague question, we begin identifying the gap logically, by narrowing the focus, defining the population, and clarifying what remains unresolved. Cancer affects millions of people worldwide, and while survival rates are steadily improving, the burden of treatment remains significant. Patients continue to face severe side effects, cachexia, fatigue, systemic inflammation, and immune suppression. Even with major advances in precision oncology, supportive metabolic and nutritional strategies remain relatively underdeveloped. That's the big picture view, the 30,000-foot knowledge gap. Malnutrition affects up to 80% of patients in certain cancer populations. And yet, structured nutritional protocols are not consistently applied in clinical care. When you look at the literature, most studies are observational. Very few explore underlying mechanisms. And even fewer are well-designed randomized trials. Now we're no longer looking at a broad issue. We've narrowed the gap, from a general problem to a specific research opportunity. Nutritional supplements such as protein, omega-3 fatty acids, and probiotics have already been studied in cancer care. But when you look closely at the evidence, the limitations become clear. Many studies are small, most are short-term, the patient populations are heterogeneous, and the mechanistic insights are often shallow. Very few trials integrate biomarker analysis. Even fewer examine the microbiome alongside clinical outcomes. Now the gap becomes specific. Not whether supplements work, but how they work, in whom, and with what measurable biological impact. So now we can clearly state the gap. There is limited mechanistic data on structured high-protein and omega-3 supplementation during chemotherapy in stage 2 to 3 colorectal cancer patients, particularly when measuring inflammatory and metabolic biomarkers. This is no longer a vague idea about nutrition and cancer. It is focused. It defines the intervention, it defines the population, and it identifies measurable biological outcomes. Now that is a testable research gap. Based on the identified research gap, we propose the following hypothesis. Targeted high-protein and omega-3 supplementation during chemotherapy in stage 2 to 3 colorectal cancer patients will preserve lean body mass, reduce circulating inflammatory cytokines, and improve fatigue scores compared to patients receiving a standard diet. This hypothesis is clear, specific, and testable. When identifying a research gap, we must avoid common mistakes. First, avoid gaps that are too broad. If the question is too general, it becomes impossible to design a focused study. Second, avoid gaps that are already solved. If strong evidence already exists, the study will lack novelty. Third, avoid unmeasurable outcomes. If you cannot objectively measure the outcome, you cannot scientifically test it. Fourth, avoid studies with no clear mechanism. A good research question should explain how and why the intervention works, not just whether it works. In research, specificity and feasibility matter more than ambition. A well-defined, testable question will always be stronger than a big but vague idea. Before finalizing your research question, pause and ask yourself a few critical questions. Is this gap meaningful? Does solving it actually improve patient care or scientific understanding? Is it novel? Are you adding something new to the existing body of evidence? Is it feasible? Do you have the tools, time, population, and methods required to realistically test it? And finally, does it connect to a real-world problem? Will the answer matter outside of a journal article? If the answer to all of these is yes, then you are ready to write. That's when your research question moves from an idea to a study. Every thesis, every grant proposal, every startup idea, and every clinical trial begins the same way, by identifying a gap. Not just any gap, a meaningful gap, a clear gap, a testable gap. The ability to recognize what is missing, and define it with precision, is what separates a reader of science from a creator of science. This skill does more than shape a project. It builds your scientific identity. Because when you consistently identify relevant, novel, and feasible gaps, you become known for asking the right questions. And in research, the right question is more powerful than the perfect answer. Strong science does not begin in the lab. It begins in structured thinking. Search carefully, analyze patterns, write precise questions, test measurable hypotheses. In the next episode, we will discuss how to design experiments that reviewers respect. Science becomes powerful when questions are powerful. If this helped you think more clearly about research gaps and hypothesis building, make sure to like, share, and comment your thoughts below. What topic should we break down next? And don't forget to follow and subscribe for more content on research, clinical science, and building strong scientific thinking.